Okay, today what I'd like to do is I'd like to solve a couple of the combustion problems that you have due in a week from this coming Friday. So the two problems I'll show the two problems that we're going to work on. The first one will be the second problem listed, 13.128 OJS. In this particular problem, we have a fuel that is made up of a mixture of different gases. And so we are given that the mixture is 75% methane, 15% CO, carbon monoxide, 5% oxygen, and 5% nitrogen. And that is the percentages. So that makes up 100%. And so when we put it in a molar analysis, we'll put it in as either kilomoles or percentage. But again, on a mole basis and not a mass basis. After we then develop our fuel, we are then going to burn it with 10% excess air. And so we'll use the software to determine not only the theoretical amount of air for all of the carbon to turn into CO2, all of the nitrogen to turn into water, and all of the nitrogen to pass through the system, and we're going to go 10% above that. It's in a reactor operating at steady state, so it's a flowing type of system. At the end, we are going to ask if the molar flow rate is 0.2. Okay, that's the molar flow rate of the fuel, and that's in kilomoles per hour. What is the molar flow rate of air in kilomoles per hour? And so we're looking for the molar ratio of fuel to air. Now, in this case, though, we have to realize that the fuel is comprised of a number of different components. Okay. You'll see in this particular case there was no calculations asked to perform in terms of how much heat release, what was the adiabatic flame temperature, or anything else. This is just from the first chapter where they were dealing with the air to fuel ratios and understanding the concept of excess air. After doing this problem, we'll look at another problem where we actually have some combustion occurring and heat release and that type of thing. So with that, we're going to bring up the test app. Okay, in this particular case, the test app is, it's a flowing system, so we're in the blue region, and it's a combustion flowing system. And so again, we could, if we had wanted to, we could have solved this problem using the mixture multi-flow mixing like we did previously. But we're going to go ahead and use the combustion. And in this particular problem, we're going to assume that we have a non-premix combustion, which means the fuel is going to be coming in and mixing with the oxidizer. And in this particular condition, the oxidizer, because it states that it's air, is going to be oxygen and nitrogen in their special proportion. And so we're going to go ahead and do the non-premix combustion. And we are now ready to tell the system what is our fuel. And as we said before, since we were given in a molar analysis, we were told that it was 75% on a mole basis of methane. I've got it set up as in a molar for the fuel. And so methane I can put in here. I can put in 0.75 if I want to. Whoops. I can put in 0.75 kilomoles of methane. And then since the next component is 20% CO, carbon monoxide, I'm going to go ahead and put that in as 0.2. And so that's my 0.02 moles of CO. I also have 5% oxygen. And so I'm going to go, excuse me, select my oxygen. And so I'm going to come down here. Let's see here. Okay, so in this particular case, it's not allowing me to put in the 5% oxygen and the 5% nitrogen. Okay, and so all I've been able to do then is put in the methane and the carbon monoxide. Okay, and so that's something that we're going to have to contend with in this particular problem. Okay. And so let's just assume that these are our two components, and it makes up, as you can see here, it should be 70%. My mistake there. This should be 70%. And I add that, and now I've got it as given. So 90% of the of the fuel has been given. And again, there's 10% that is oxygen and nitrogen. And so we're going to actually add that a little bit later if we wanted to do this particular problem. And so now that we've selected our fuel, we're going to go over to the oxygen. And now we're going to say that we're going to assume that the nitrogen and the oxygen were there. And so we're going to put those in as 0.05 moles of oxygen and 0.05 moles of nitrogen, okay, to be consistent with what we put in for the fuel. Now we have the 100% of what the fuel is. Okay, so now with this in mind, we're now going to tell the software that we want to burn this completely with 10% excess air. And so the action that we're going to select, excuse me, is a complete combustion with known excess air. And so with that in mind, I'm going to move this out of the way, set this down here. And so our ratio here, this is the ratio of theoretical air, which I'm going to allow to be 110%, which is 10% excess air, and I'm then going to execute it. And so upon doing that, what has happened is one has seen that the oxygen and the nitrogen have been included, and just enough for there to be complete combustion. Now, having done this action, what has happened is the software has taken a look at what the fuel was and has gone through and balanced the stoichiometric equation and made sure that there was 10% extra oxygen associated with the system. So if I were then to take a look at the equation, okay, this is what I put in. I put in 70% methane and 20% CO2. And what it wanted to do, and what it does, is it takes the fuel and it makes the fuel 1 mole of fuel products. And so that's why these two add together to be 1 mole, and they are in the 70-20% amounts. And so upon doing that, then it looked and it saw, okay, if I had gone back and if I would have executed a theoretical combustion with that, what it would have come back with is the same proportion. And now this is the oxygen and the nitrogen that was just enough to cause all the carbon to turn into CO2 and all the hydrogen to turn into water and the nitrogen to pass through. And so that would be the 100% condition. But we're going to go ahead and I'm going to redo that. I'm going to say that it was complete combustion with 110 excess. And so I execute that, and we see that now it is the same components as the fuel, but now there is that 10% more of the oxygen and the nitrogen. And that 10% extra oxygen shows up over here, and the nitrogen passes through the system. And so the question that is posed in this problem is, if the molar flow rate of the fuel is 0.2 kilomoles per hour, what is the molar flow rate of air in kilomoles per hour? And so what it has done is it has calculated the moles associated with the fuel here and the moles associated with the air, and it's already calculated that air to fuel ratio. And so this 1.83 plus 6.89 adds up to 8.73. And that is divided by 1, which is the number of moles of the fuel. And so the answer to this problem is the ratio, this 8.73. All we'd have to do is multiply 0.02 kilomoles per hour of the fuel by that 8.73, and that would then give us the answer to this particular problem. Now again, that is assuming that our fuel, as we had set up here, only consisted of those two components. And our oxidizer was just oxygen and nitrogen in the proportion that air delivers. And what we don't have in this particular problem, though, is the fact that the extra oxygen and some extra nitrogen is also present. Okay? And so when you look at this equation here, then what you are saying is, if I put in some extra oxygen and some extra nitrogen, I would have to make sure that I put it in with the right ratios associated with these two components, and then see what would happen then to the other components. And so there is kind of a way to do this, and I wanted to use, for right now, this particular problem, let's just suffice it to say that the molar air-to-fuel ratio has been determined, and the fact that there's some extra oxygen and nitrogen in the fuel would change the answer slightly. But I wanted to show, what if we wanted to add the right amount of oxygen and nitrogen that shows up in the fuel. And so there is a executed action here that we can perform, and we can change. We can multiply every one of these numbers by a constant. And what I want to do is I want to turn this CO and this CH4 into the corresponding 70 and 20, so that it represents in whole numbers the value associated with the moles of each of those individual species. And so I'm going to do that by multiplying each term by 70 divided by 0.778. And I'm going to show you what happens when I do that. So it's called multiply by a factor. And the factor is going to be 70 divided by 0.778. And so I could either do the calculation, or I can have the system do the calculation, and I do an execute. Okay, upon doing the execute now, what you see is the balanced equation now is 20 COs, 70 methanes, along with the corresponding oxygen that causes the water and the CO2 and the extra oxygen to show up. And so now I have a balanced reaction. Now you'll notice that the air to fuel on a molar basis stayed the same. But by doing it this way, I now can see that in order to add 5% CO, or 5% oxygen and 5% nitrogen, here all I have to do is make this number 170 and this number 625. 165 is going to go up to 170, and 625 is going to go up to 625. 620 is going to go up to 625. And so what that will do is that will then add the 20 parts of oxygen and the 20 parts of nitrogen to the 5 and 5 to the 20 and the 70 here. So how do I'm going to do that? I'm going to now go back up to my oxidizer. And now for my oxidizer, what I'm going to do here is I'm going to change this. This 164.9528 is now going to be 164.98 plus 5. Okay, so I added 5 units to that. And now I have the 620 that now is, I have the 165 that's now turned into 170. And now my nitrogen is 620.22, and so that's going to be 620.22 plus 5. Got to make sure I get 620 plus 22, and that's add that. And so now I have on my balanced equation here, I now have my 70 parts, my 20 parts, I have an extra 5 parts here, an extra 5 parts here, and I've put in enough oxygen and nitrogen to be 10% excess air. Now you'll see it's not balanced yet, and so there is an action that allows me then to complete the combustion with user-specified oxidizer. And so the user-specified oxidizer is what I just modified. I modified the oxygen and nitrogen and I'm going to then select that and do an execute. And so upon doing that now, you see now what it's done, again, is it likes, anytime you do one of those actions, it likes to go back to 1 mole of fuel, okay? But if I were to do the same thing we did before, to make this 778 turn in to, I can now go back and do a multiply by a factor, and I can use the same factor I had before, again on those two fuels, and execute. And now what should happen is now I'm back to the equation that I wanted. And I also then did a balance. I did a balance on the products. And so now everything is perfectly balanced. And that then is the true answer to the question. So the true air to fuel ratio on a molar basis are these two added together divided by these two added together. And so you see that it's really like 13% of 13% excess air. So this was a little bit tough problem, and what I use this problem to kind of highlight what can be done in these tasks. We can do theoretical combustion, whether we're using air or pure oxygen, theoretical combustion with user-defined oxidizer, or we can add deficits or excesses. And then we had to do, like that in that last case, we had to do our own balancing due to the specified oxidizer. And then it also allows us to do this normalization and multiplying by a reaction, by a factor. Okay, so with that done, I'll stop at this point.